Good evening, everyone, and welcome to Sydney Ideas, the University of Sydney's flagship public talks programme. I'm Alice Motion. I'm from the School of Chemistry and an Interim Director of the Sydney Nano Institute here at the University of Sydney. So it's my great pleasure to welcome you this evening. I'm absolutely thrilled to be your host for our public event, Nanotechnology, Scalable Solutions for Climate Action, which is presented together with Sydney Ideas and Sydney Nano. Before we start and I introduce you to our fabulous panel this evening, I would of course like to acknowledge the traditional owners of the land on which we meet this evening, the Gadigal people of the Eora Nation. There is no place in Australia, water, land or air, that has not been known, nurtured or loved by Aboriginal or Torres Strait Islander people. This always was and always will be Aboriginal land. So it's my great pleasure to introduce you to three of the wonderful colleagues that I have at the University of Sydney, three fantastic professors who I'm going to tell you a little bit about in just a moment. Tonight's conversation is all about what nanoscience is doing to pave the way for new and better renewable technology. And I think just before we go into the nanoscience, just a little bit of a reminder of the scale that we're talking about here. So we're talking about 10 to the minus 9, a billionth of a meter. So this is a strand of DNA. If you think about the diameter of that is about 2.5 nanometers, but maybe something that we're a bit more familiar with if we think about a typical human hair. Sorry for the audio issue, I'll try and moderate. If we think about a typical human hair, that's between 50,000 and 100,000 nanometers in diameter. So it's really very, very tiny. And ironically, to see things that are very tiny, we often need very big machines. So tonight we're going to be looking at what's happening in each of the areas, what the public may not know about some of these technologies, and what we need to do to implement them next, because it takes a while to take research ideas that are being explored in a university setting and to take them out into broader applications. And we have three wonderful experts here who are working across, they're all part of the Sydney Nano community. They're also part of Faculty of Engineering, the Faculty of Science, and they're working in areas that span carbon removal, solar power, and clean hydrogen. And I'd like to introduce them to you now. So I might start with the person furthest away from me. So Professor Deanna D'Alessandro is a chemist and a professor at the Schools of Chemical and Biomolecular Engineering and Chemistry. So two schools and two faculties for Deanna. And she's also the director of the Faculty of Engineering's Net Zero Initiative. This is a really exciting new initiative at the university, which aims to help the government, industry and communities manufacture, deploy and adopt cost-effective, low-emissions technologies at scale. Deanna has over 16 years of professional experience in materials science. She's a passionate interdisciplinary scholar and really wants to bring these interdisciplinary efforts together to address climate change through net zero and negative emissions technologies. Please welcome Deanna. Next, I'd like to introduce you to Professor Francois Aguey-Zinsou, who is a professor of chemistry at the University of Sydney, and he leads the Merlin, so we've got something that sounds like a wizard here, the Materials Energy Research Laboratory and Nanoscale Group at the School of Chemistry, with over 20 years of experience, and he's one of the leading experts in hydrogen technologies. So please join me in welcoming Francois. And finally, immediately to my left is Professor Anita Ho-Baillie. Anita is the John Hook Chair of Nanoscience here at the University of Sydney. She's also an ARC Future Fellow and an adjunct professor at the University of New South Wales. Anita's research interest is to engineer materials and devices at the nanoscale to integrate solar cells into all kinds of surfaces to generate clean energy. Anita is a very highly cited researcher and has been identified as one of the leaders in advancing perovskite solar cells. We'll hear more about those later. And Anita's achievements in setting solar cell efficiency world records in various categories have really placed her at the forefront of her research. So please welcome Anita. Let's get started. And first of all, I would like to go to Anita, but I'm going to ask each member of our panel to take a moment to introduce yourself. I've given you a formal bio, but we'd like to know a little bit more about you and your role at the university. And we'd also really like to know, if you can put it as simply as possible, what is the technology that you're working on? So Anita, let's go to you.
Sure. So I'm based at Sydney Nano Hub. The microphone doesn't seem to work. So I'll just use this. Okay, so you can pass it to Alice, I guess. I'm working in the next generation solar technology. So the solar technology that we have on our roof or in the solar farm is based on silicon. So our solar cells within the panel is made of silicon. So it's a fantastic technology. The cost of silicon solar cell has gone down by 10 times in the last 10 years, and really at the moment is the cheapest way, or the cheapest renewable way of generating electricity. But it's got a limit to it. So the highest efficiency we can ever get, theoretically, is going to be 29%. So where does the 60 or 70% gone? A lot of it's gone into heat, and that's because silicon's got a limited way of absorbing the sunlight. So we've got this thing called the band gap, and it limits the amount of energy the material can absorb. So you have sunlight with a photon energy that is spread across the spectrum. So for example, you have blue light, you have red light, you have green light, and you have orange light. So blue light is very energetic. And when silicon solar cells see the blue light, it will absorb the sunlight. But because the photon is so energetic, a lot of the energy is wasted. So it turns into heat. So you have solar panels that gets hot. And then you have light that is perhaps infrared, and the energy in the infrared light is actually lower than the band gap of the silicon. So it just goes straight past the silicon solar cell and therefore doesn't get absorbed. So therefore, we're working on the next generation solar cell technology where we engineer the materials to have different band gaps, so they are tailored to different photon energy. So we stack them on top of each other. So we will have a blue cell, and then a green cell, and an orange cell, and a green cell, and then a red cell. So we call this a multi-junction solar cell. So silicon on our roof is single junction, and when we move on to double junction, then the efficiency will jump up to 40%. And when we move to triple junction, the efficiency will jump up to 50% and so on. So that's what we're working on, and we will talk about how Nano comes into this technology.
And Anita, is there a prediction of how far we could go in terms of efficiency? Is there a limit to the efficiency we can get with those solar cells?
Yeah, so you can keep increasing the number of junctions, but as you increase the number, the improvement gets incremental. So it gets to around 60% for 6 junction, but it gets very complicated after that. And of course, there's some fundamental limits to the solar cells. So you have losses that you can't quite get rid of because of thermodynamics, because the sun is really hot and your solar cell is not as hot. You have emission losses where you get the sunlight from a broad angle. You get sunlight from a sort of a narrow angle, but then it radiates back into a broad angle, so you get those losses. So any solar cell is an absorber, and when you have an absorber, it always emits light as well. Mm-hmm. So you get those losses you can't quite get rid of. But anyway, we're working towards hopefully 50% efficient solar cells. That's what we want to achieve.
Great. We'll hear a little bit more about that in a moment. Thank you, Anita. Mm-hmm. So, Francois, could you tell us a little bit about you and your role at the uni and your technology?
So, and my microphone is working, so that's good. So a solar panel is great, but the sun is only shining during the day. And so you probably know that there are batteries around, but batteries don't have a very good energy density, which means that you cannot store a lot of energy. The best battery we have today are lithium-based. We are all using them, for example, in our mobile phone. They are good for running mobile phone, good for running electrical bicycles and the like, light-duty vehicles, but they are not very good for storing energy for long term and for storing a lot of energy. And this is where hydrogen is very exciting, because not only you can use renewable, but then you can convert that electricity into hydrogen. And hydrogen is something we can store. We can store hydrogen for a million years and go to use that energy again. And hydrogen is clean. So this means that we can substitute fossil fuel, because fossil fuels not only provide energy, they also do a range of services. For example, we use them to make clothes. We use it to make drugs. We use fossil fuel also to make chemicals. Hydrogen is also a precursor that we can use in the chemical industry. Hydrogen is something we can also use to produce heat. A battery cannot produce heat. For example, for some processes to make bricks or to cook the best bread, whatever is the story. So really what we are working on in my lab is understand how we make hydrogen a fuel that can be used across industry, but that can also be used by individuals. So we develop technology to produce the hydrogen with electrolyzer. My microphone is gone. And we also develop technology to store hydrogen as a form of a solid. So I'm sure all of you have heard about a hydrogen disaster, and all of you are probably scared of hydrogen. So what we are working on is storing hydrogen as a solid. Not a compressed gas anymore, but in material as a solid. So this makes the use of hydrogen safe, because those materials store hydrogen within their structure, and they cannot simply release the hydrogen like this. And what we are working on also is developing a parent technology called fuel cells, and what we are interested in is enabling those technology, for example, to be 3D printed. So any of you can go to 3D print a fuel cell, can go to 3D print an electrolyzer. You don't need to be a scientist like me or an engineer, and plug and play. You know, a solar panel is nothing complicated to install on the roof, as long as you don't fall off. And that's the things that really excites me. So I should stop here, otherwise I can talk forever.
Thank you, Francois. And maybe we'll see how Deanna's microphone goes, but we may pass that one along. Deanna, would you be able to share a little bit about yourself and your technology for us now?
Yes, so here goes the experiment. So look, I'm a chemist by trade, and I guess I've been fascinated with atoms and molecules most of my life. And I guess that really is the heart of why I work now with one of my hats on. I think we might need that, Francois. One of my areas of work is applying the nanomaterials I make, which are called metal organic frameworks, or MOFs for short. And these are highly porous materials that we'll get to a little bit later. But what's really exciting about these materials is that because of their incredible structural and physical properties, they have really interesting applications across a broad suite of areas. So one of the areas that we were going to talk about this evening is the area called direct air capture. And so what I mean by this is these materials can actually remove, in our case, greenhouse gases from the atmosphere, but they could be used to store hydrogen. They could be used as catalysts to convert one molecule into another molecule. They have actually been used in solar cells as well, and there are some close analogies between the structures of the materials I work on and the structures of the materials that Anita and Francois work on as well. So really, as a chemist, what excites me is the fact that we can design these materials, we can synthesize these materials, and we can do so in a way that makes them really highly tuned for the particular application. In our case, as I said, removing 0.04% of carbon dioxide from the atmosphere, which is this application called direct air capture that we'll talk about as we go on.
Thank you, Deanna. So we might come back to you again with question 2. I would like to just open the question about how did you come to to research this particular technology? What drives you to research this? And why should we as an audience who care about our climate, the future of our planet, the future of society, why should we care about your technology?
Well, I think the first thing to say is it didn't start with the technology, and I think this is the critical interplay between fundamentals and applied. Actually, where it started was the discovery, not in my lab, but in labs around the world, one of the labs in America where I did my postdoctoral training. It was the discovery that we could, in fact, design and synthesize these materials, the development of the methodologies, if you like, to selectively make these materials and make them in a way that they could be highly selective for particular gas molecules. It was actually that discovery, that the fundamental discovery, if you like, that very much comes from just a desire to understand how atoms can be arranged in three-dimensional space. It was actually that really inspired the application. And then, of course, you realise what you can actually do with these materials that are ultra-high surface area materials, and we have some pictures a little bit later. And then, of course, the potential of the application becomes apparent, and then you have this really close feedback loop between fundamental and application, and all of a sudden, the world explodes with these materials as we have as a scientific community.
Thanks, Deanna. And for you, Francois, why do you care about your technology? Why do you think it's important, and why should we?
I think the answer is quite simple. I'm born in Africa, in Benin, so this is not one of the richest countries on the planet. And as you probably know, if you don't have access to energy, simply to be able to read at night when you come back from school to be educated, then life becomes difficult. The thing about hydrogen is that you don't need to have access to fossil fuel. So if you are a country where you don't have fossil fuel reserves, you can produce hydrogen from anything, from biomass, waste biomass that you may have, organic food, or the leftover from your dinner, you can produce hydrogen from it also. You can produce hydrogen from renewable energy. And this is, I think, what is very exciting for me. This means that you can provide to people across the planet means to generate their own energy.
Thank you, Francois. And Anita, same question to you.
Right, so I've got two answers. The first one is, I guess, no doubt solar is going to be the future source of energy. Because we want to move away our reliance on fossil fuels because what carbon dioxide can do to our climate. But I'm also deeply inspired by solar. So when I was an undergraduate student, I never thought I would become a solar scientist. So I was going to be an electrical engineer. But one of our professors, he sneakily just put in some solar cell material in our electrical engineering circuit course. And he took us up to the roof of the building and he showed us a solar panel connected to a water pump. So he removed the cardboard and you can see the water pump start pumping water. And the only way to stop it is to put the cardboard back on, and there's no power point. So when I saw that, I was absolutely inspired. It's free energy from the sun. And after that, I remember in my first year of PhD, we took a group of 15 undergraduate students to Nepal, where we install a solar battery system for a remote medical clinic that serves 30,000 people in the region. So just a simple solar battery system will give them lighting. So at night, if people like women in labor, they come into the clinic, they can see. Just simple things like that can improve people's lifestyle so much. And so the second higher uptake of solar is in a lot of third world countries still, where people are able to read at night. Simply having a solar system, a solar battery system, allow women to read at night and children to read at night, and that's very valuable.
Thank you, Anita. So we're going to zoom in on the nano component of each of your research, of each of your areas of research now. And I think we have some images to help us with this. So we'll start with you, Anita. We have some images to help us understand a little bit more about your technology. Can you explain to us a little bit more about the nano component and how it works?
Sure. So I'll just step you through what we're looking at first. So on the right-hand side, it's a little double junction tandem solar cell that we make in our lab. So sitting on the grass, and it's powering a little windmill in front of, that's not Hogwarts, that's University of Sydney. And on the left-hand side is a schematic of what that double junction solar cell looks like. So you can see, maybe it's not very clear to you, on the bottom, you can see the grey thick slab, and that's silicon. So that's the silicon solar cell that we all have. That's the incumbent technology on our roofs or in the solar farm. And then on top, we stack a perovskite solar cell. So the perovskite is made of metal halide perovskite. So perovskite is just a description of a crystal structure. And the particular perovskite we work with is a metal halide perovskite. So it's a very good material. It absorbs light really, really well, and therefore we need a very thin layer of it to stack it onto the silicon. So where the nano component comes from is in those yellow and also blue layers where we have to interconnect the perovskite cell, the top cell, to the bottom silicon solar cell. Also, where the nano component comes from is from the top of the solar cell where you have the sunlight coming in. We can put nanoparticles there as well to steer the light into the solar cell. So why nano? When we get down to very, very, very small stuff, we found that the physics and the chemistry don't work necessarily classically. And we can make use of those non-classical properties to engineer the way the light works and also to engineer the electrons work. So we can engineer the way they go into the solar cell and also engineer the electrons flow through the solar cell.
Wow. And how do you make those layers? What sort of techniques are you using in your lab to manufacture these nano-impregnated layers?
Yeah, so now, actually nanoparticles is not something new, really. I mean, gold nanoparticles have existed, in centuries, and you can see, oh, wow, different size of gold nanoparticles will give you different color effects. The way we make them is by physical deposition, so there are various ways of depositing things onto something. So you can do it by solution. You can do it by spraying, you can do it by spreading, you can do it by spinning. You can also inject energy into the particles so that it can go from one place to another. You can also evaporate things. For example, if you heat up metal under low vacuum, it will have a high vapor pressure, and therefore it can evaporate much easier than you would have in a normal atmosphere. So there's various ways of doing that. You can also do atomic layer deposition, where you can control the deposition at atomic scale.
So lots of different methods for making these layers. Thank you, Anita. We're going to zoom in on Francois and his research now. So we're going from those sunny lawns of the University of Sydney into understanding what's happening in these hydrogen-focused laboratories. So, Francois, take it away.
So, I'm not going to run through the entire slide, but typically, to come back to some of the technology we develop in stored hydrogen, we use material to do that. So here you have a range of material, LiBH4, MgH2, LaNi5, and those materials on that picture, they show you typically the energy density you have versus the power output that a man or a woman can deliver every day. So before we had oil, we had slavery, right? So we don't necessarily want to go back there. So oil gives you the equivalent of about 16 days of somebody doing work. And this is a machine doing that work now. So the question is, if we can develop the best battery, that's about the work of 0.3 days of somebody working. So you can see that the best battery is not going to get us to go there to actually replace fossil fuel, because fossil fuel can help us to do much more work than what we can do with a battery. If we look at 1 kilogram of hydrogen, this is equivalent to 49 days of somebody working. So you can see that there is a lot of energy in hydrogen per kilogram. But the problem with hydrogen, it's a gas. So the energy per volume is very low. And this is why we use material to store this hydrogen, so we can increase the amount of hydrogen we store per volume. Where the nano component comes in is that when hydrogen comes to those materials in the form of applying hydrogen pressure, the material will start to suck up the hydrogen, like a sponge that you could put, for example, in a bucket of water. If you take a dry sponge, you put it in a bucket of water, the sponge will start to absorb the water. The material here do exactly the same. You put them under hydrogen pressure, so you put above the atmospheric pressure, those materials under pressure, and they will start to suck up the hydrogen and store the hydrogen within their structure. Where the nano component comes is that when you start storing hydrogen within the structure, you want to do that under ambient conditions, so you don't need to have any energy input. And some of the material that can store much more hydrogen than lanthanum nickel 5 here, which is at 0.7 day of man work equivalent, we would like to have a material at 7.4 day, so we can start to go to compete with oil. They can only do that at relatively high temperature, so 400, 500 degrees C, which is not ideal because this means that you need to have another heat source. What we think, and the theory my group has been working on for some time now, is that if we actually make those materials at very small scale, then exactly like what Anita mentioned, the rules of the chemistry and physics are different, and the way hydrogen interacts with those structures is very different. And this means that we can start storing hydrogen at the ambient in those materials. And this is very exciting because this means that we could develop technologies where we could store a lot of hydrogen in a very safe way.
Thank you, Francois. Deanna, over to you. Let's have a closer look at some of the technology that your team and others are developing.
Yeah, thanks, Alice. So, look, there's a little bit to unpack here, but at the heart of it is the nano. And so the little spinning picture that you see there is actually an atomic, it's actually an X-ray crystal structure, and we get these structures by basically firing electrons at the material and watching how the electrons deflect and diffract off the crystal planes. And so what we get out of that is this picture, and every little sphere that you see there, the grey balls, the red balls, the blue balls, is an atom. And what you'll notice about the little spinning picture is that there are holes inside that particular material, and those holes are on the nanoscale. And what's particularly exciting here is that it's an ordered structure, it's a periodic structure. Actually, perovskite is one structure type that can also be adopted by these metal organic frameworks. And it turns out that inside all of those little nanopores, that's like a house in which can reside gas molecules or other guest molecules like liquids. And so basically what we're doing here as chemists is designing the atom placement. And by designing the atom placement, we can actually design how that material interacts with what we call adsorbent molecules like carbon dioxide or methane or what we recognise as the greenhouse gases. And so that nanomaterial is really right at the heart of one of the technologies I work on, which is direct air capture. And I didn't mention before that the reason why this is important is that we have 3 trillion tonnes of carbon dioxide in the atmosphere that was put there since the industrial age. And the latest Intergovernmental Panel on Climate Change report, just released a few weeks ago, shows us that to reach net zero, it's not going to be enough just to implement renewables and mitigate current emissions, that actually we also have to deal with the existing legacy emissions in our atmosphere. And so we need a portfolio of approaches, and this is just one of the options alongside the other technologies that we're talking about this evening. So you can see the correspondence here with solar, because actually the process that I work with my industry partner, Southern Green Gas, on is powered by solar. So right at the heart of, you can see it looks a little bit like a two-person tent, where the solar panels form the A-frame, and underneath that A-frame is where all the action happens. And so we have canisters that contain our metal organic framework sorbent. We use fans to draw in, and this is now getting to the macro scale, but this is the interfacing of the nano with the macro. And those materials are very highly selective for carbon dioxide. They absorb the carbon dioxide, and hence we can remove carbon dioxide from air.
Thank you, Deanna. And we'll go back to you now. So my final question for each of you before we go to the audience is that you've each shared some really exciting technology, some great nanoscience. I'd like to know a little bit more about what are the challenges for your technology now. And I'm thinking both on the technical side, but also on the social or the political side. What would jeopardize, both technically, socially, politically, you being able to bring your technology into a place where we can use it and make sure that it's holding true to its promise in trying to reduce, remove, some of the impacts of carbon dioxide on our climate. So, Deanna, for you first.
I think there's probably one word, and that's scale, because the scale of the problem is immense. We know that by the middle of this century, all of the modelling is showing us that we need to be removing something like 10 to 20 gigatons of greenhouse gases from our atmosphere in order to have a hope of moving toward net zero future. And so the scale of this is enormous, and it requires all hands on deck. And it requires that our technologies can come down the cost curve, because at the minute they are very costly. Making these nanomaterials on the scale that we need to make them is a challenge. So these are all the technical challenges of scaling. And then on the other side of it is the policy and legislative challenges. So, for example, there is no policy nor legislation in New South Wales to actually use this technology. And the reason is that once we take the greenhouse gases out of the atmosphere, we need to durably put them somewhere or do something with them. And at the moment, there is no legislation to enable us to do that. There is in other states of Australia. So that gives you just a flavour of some of the challenges, not just at the nanoscale, but actually also at the socio-political and economic scale.
Thank you, Deanna. Francois.
What was the question again?
So we've heard about the great promise of some of these technologies and the fantastic science, but what are the greatest technical, political, social challenges for hydrogen?
Well, I can take this in different direction. I think I'm a dreamer, so for me, I would like to see this technology that we are developing being made free for all and the benefit of the community. Now, you may have heard a lot about hydrogen in recent years with a push toward setting up Australia to export hydrogen globally. I'm not sure we are there yet. I'm not sure by 2050 there will be a global market export. These are business as usual for me. For me, the real challenge is we have climate change issue in front of us, and we need to accelerate how we develop technology and commercialize those technology and find the money for those technology to reach to the community and really understand how those technology could benefit to the community. So for me, I think it's a different agenda that is not necessarily understood, and this is where I would like to see some progress.
Thank you, Francois. And Anita?
Yeah, so for our technology, being able to be as good as silicon in terms of the reliability, that's one challenge. Silicon itself is quite a good optoelectronic material, but it's not the best. So with perovskite, optoelectronically, it's actually superb. But in terms of reliability, solar panels got to last for 25 years now, 25 years time now, and people may be even talking longer lifetime. So with perovskites, we need to stabilize it. We need to make sure that it doesn't degrade over a long period of time, and that's one of the challenges. So 2 years ago, we managed to stabilize the perovskite cell to pass 3 industry standards for humidity and heat. and we would like to put more work in so that it's also stable under heat and light at the same time. So that's one of the technical challenges we've got.
Thank you very much. So we're going to take some questions from the audience. If you would like to ask a question, we have two lovely people who are going to be roaming with mics. While we're waiting for some audience questions, there's a few great ones on Slido. I would like to go to a question. So first of all, somebody did say, "May the 4th be with you." I missed the opportunity to say that, so thank you for the anonymous person who shared that. May the 4th be with you all. I might go with this one. If someone gave you a check, each of you, a check for $1 million, what would you do with it to advance your research? So.
That's easy. I will use the money to set up an international research lab so we can accelerate and leverage on that money.
Great, short answer. Deanna?
I think I come back to scale because that is the biggest question. It's always the first question everybody asks, and so we would work it, use it to scale up our nanomaterials and demonstrate how that can be done, and I guess really connect with the international researchers, develop a sort of a network to deal with the sort of ecosystem that we need to develop within which our technologies need to be, the socio-political and economic considerations that go into actually implementing our technology responsibly with the communities within which their backyards will be, will have these technologies.
Thanks, Deanna. And Anita, over to you. No pressure, because maybe this person has $1 million that they'd like to give to one of you. So, but what would you do if you were given $1 million to advance your research?
Probably to solve the hardest problem. So in our case, will be for the perovskite to have the same reliability as silicon.
Person in the green scarf, go ahead.
Hello. Oh, gosh. Okay. Deanna, I have a question for you about, you mentioned the legislation that was put forth in other states and not existing in New South Wales. I was just curious on what the legislation was about.
The legislative challenge that we have is around what we do with the carbon dioxide once it's removed from the atmosphere. So there's a number of things you can do. There's a fabulous company in Newcastle called MCI, who are actually turning the carbon dioxide into building materials, because you can basically do some nifty chemistry and you can react carbon dioxide, which is an acid, you can react it with a base and you can make a solid material, usually a carbonate material. So that's using it to do something useful. You can make food and fuels out of it. It's essentially a sustainable source of carbon. But the challenge comes when you actually want to durably store the carbon in another way, for example, underground. So geosequestration is essentially carbon storage underground. Essentially, we extract fossil fuels from the ground, and the idea here is that they've been there for hundreds of millions of years. Well, why can't we durably store this excess greenhouse gas in the atmosphere underground? So a number of ways we can do that. We could do it in depleted oil and gas reservoirs. But the challenge there is that oftentimes what happens is they use the carbon dioxide to actually push out more in a process called enhanced oil recovery. So in our direct air capture process, there isn't a connection at all with fossil fuel users or producers, and actually the geosequestration we're looking at is geosequestration into porous basalts, of which Australia has some incredible opportunities to durably store greenhouse gases safely. So the legislative issue is the fact that we can't do that in New South Wales, but there is a lot happening, and importantly, because we understand a lot about other legislations in other jurisdictions around Australia and internationally, that really what we're trying to do is develop that legislation and policy in a way that is socially, ethically and environmentally responsible.
And Deanna, just a small follow-up question there. If you're able to store carbon dioxide, as you mentioned, safely, in a way that that is environmentally benign, would you then be able to release that carbon dioxide when you wanted to use it, or is the idea to to keep it stored? You know, what's the plan for the release or storage time period of the carbon dioxide?
Yeah, so durable storage in our area is really 1,000 years plus, and there are actually companies around the world doing this. So, for example, a company called Climeworks, which was probably the foremost direct air capture company in the world in Northern Europe, the carbon dioxide actually turns into rock once it's pushed underground. It reacts with water and it reacts with minerals in the soils and within the rock formations, and it essentially turns into rock. So no, you can't reverse it, and that's the whole idea. It's actually the durability and the non-reversibility of that process that will keep it stored for, quote, geological time.
Thanks, Deanna. Any more questions? There were a few hands that shot up before.
Can you hear me now? All
We
right,
can.
cool. I was going to ask about the impact of water supply to the availability of the technology, because I know, Francois, you're from Africa. I know you probably know a lot more about places like the Sahel region than myself, but I know that West Africa is basically going to be the mining capital of Earth for renewable technologies. But I know that water goes into a lot of mining, so I was just wondering what kind of challenges and solutions we have for that going forward.
You are right. I think the problem is not water per se, but it's how water variation are going to occur in the context of climate change. And the good thing about hydrogen is that if you do it cleanly, you use water and you produce water. So it's a closed loop, more or less. Now, obviously, in this country, we don't drink the recycled water. I think we will have to at some point to be able to cope with variability. And then there are desalination technology. This requires energy. But I think the water problem is really, again, a problem of society on how we manage water and how we manage water well and what we do with that water. So water is used in industrial processes, but water is also used for food, agriculture, and is really on how we recycle that water and we better manage our resources. So it goes back to the bigger question on how we manage the environment, our environment, and how we manage the resources that we have around us.
Thanks, Francois. Anita?
Yeah, so it's a good question. I mean, water goes into semiconductor processing and uses a lot of water. So a lot of technology use water for cleaning stuff to make sure there's no impurities. So Francois and I have been talking a lot about our next generation technology. Okay, well, we improve the efficiency of solar cell, we stabilize, we make them durable, but is that the end? Are we able to design something that is easily recyclable, that is easily reusable, and maybe uses less energy, less water, less material? And, you know, we also look at circular economy. So I've got a student looking at circular economy. So the standard way of looking at circularity of something is look at the materials in mass that you can recycle. But at the moment, we're looking at the energy consumption. So we sort of have this new matrix, which is circularity based on energy, based on electricity. And the next thing will probably be circularity based on water. So yeah, this is a very interesting topic, and this is something that I think the next generation scientists and engineers, when they come into the lab, they don't just work on a silo problem and just work on improving this little thing, but they have to think more about the overall sustainability.
Thanks, Anita. I think we've got time for just one more question. I'm sorry, we've got a person in red at the back, but if you want to come and ask us at the front, you're very welcome. Just trying to keep to time. So we've got one more question from the person in red.
Thank you. I'd like to know if you have to keep some of your work secret, because you're heading towards, if you invent the light bulb in your field, you will have to then sell it, and obviously Australia will benefit. So is there pieces of the work that we will never hear about?
So something about the secretive nature of your work. So maybe a brief response from each of you on this one. What are the secrets that you're hiding in your laboratories?
Well, you might not hear about it, but you'll see it in action. So although sometimes, yes, you're absolutely right, there is secret know-how, and then there are different levels, I guess, of IP, and those are protected to different extents. In our work, we have everything from secret know-how all the way through to IP that's protected, and then, of course, work that we share. And in fact, even work that's protected by IP, because of this, and I started out by talking about that really fundamental loop between the fundamentals of the nano, of the chemistry, and the applied, that really underpins all of this. So we definitely try to let the world know, because knowledge creation, you know, we stand on the shoulders of those before us, and as the generations go on, as our children, you know, step into the shoes and lead this world, then they need to understand, you know, the knowledge needs to grow as we go on. So we definitely share what we can as well.
Francois?
Obviously, we have a lot of secrets. More seriously, I think the point you are raising is a sovereignty issue. So obviously, when you are talking about the field of research in which we are working, for nations that can control the technologies, they will control key aspects of future market. Energy is not a market like any other. If you don't control your energy supply, you don't control your economy. It's as simple as that. So beyond this, as scientists, we share ideas within our communities. Obviously, we don't tell all our secrets. And if we come up with a light bulb moment, usually then we get bodyguards. And so, because we never know. But then between the discovery, what you have to keep in mind, there are two different things here. Between the discovery and the commercialization, and this was a comment before, there is a long journey. And these are very two different paths. Usually you have bright scientists that discover something, and it's somebody else that managed to commercialize the technology. So these are very two different paths.
Anita, any secrets?
I'm not telling you. Yeah, that's a nice balance, isn't it? You know, there are advocates for open access, you know, all the scientific knowledge should be made available. And when people want to exploit that opportunity, they may want to be the first to do so. So, yeah, that is a tricky question. So when we think that we may be able to, in that position to exploit the technology commercially, yes, we do try to protect it as much as possible, either by saying, this is mine, and if you want to use it, please ask, by protecting it, or we simply don't share the information. So, yeah, so this is what we do usually.
Thank you so much. I think what's really clear is that with wicked problems, like the ones we're discussing tonight, we need as much collaboration as possible, but sometimes in order to commercialize something or to make it useful, you also have to balance those things. But we're all, I know certainly the panel here this evening are all about collaboration with people around the world as well as across Australia. Thank you all very much for joining us this evening. It's been a pleasure to be with you. I'd just like to, before I send you out into the night and wish you a lovely evening, I'd like to welcome you to come to the next Sydney Ideas event, which is on Monday the 22nd of May. It's Voices on the Voice, so it promises to be a really interesting and important discussion. So please join us if you're able. And I'd just ask you to join with me in thanking once more our panellists this evening, Deanna, Francois and Anita.